Hey, this is Math 6, Unit 2, Lesson 3. It's called Recipes, and we're going to explore how ratios affect the way a recipe tastes. And for some of these things today, it might be good if you actually experimented with some of these recipe ideas, just so you could taste the difference and kind of get a hands-on experience of what that's like. For this video lesson, I won't be doing that because it would just be you watching me drink Kool-Aid and things like that, which doesn't sound very exciting on a video. So here we go. First off, we had the flower pattern. So the flower is made up of yellow hexagons, red trapezoids, and green triangles. Write sentences to describe the ratios of the shapes that make up this pattern. So we could look at first of all with the yellow hexagon. The yellow hexagon, we have 1, 2, 3, 4, 5, 6 of those. For the red trapezoid, we see we have 2 of those. And when it comes to the green triangle, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 of those. All right, so some sentences we could say. We could say that for every 2 trapezoids, there are 6 hexagons, right? That's a true statement there. Are there others you can make? Absolutely. You can make notice of how many triangles there are. There are 9 triangles for every 6 hexagons. There are also 9 triangles for every 2 trapezoids. There are 2 trapezoids for every 6 hexagons, and vice versa. So there are lots of things you could do there, but you need to write a couple sentences there with your partner, or check with your partner, see how you do. And that's it. Question 2. How many of each shape would be in 2 copies of this flower pattern? Okay, so initially, for 1 copy of the flower, we have the hexagon, we have the trapezoid, and we have the triangle. And let's just draw a little table here, mark this out. So when we had 1 copy, we had 6 of them, we have 2 trapezoids, and 9 triangles. So if I wanted to make another copy of that, if I wanted to have 2 of those things, I would have to basically double the value of each one because I'm going to have 2 copies. So instead of just 6 hexagons, I would end up with 12 hexagons. Instead of just 2 trapezoids, I need 2 more for the other one, so I end up with 4. And instead of 9 triangles, I ended up with 18. So when I'm going to make a copy of something, in this case here, because I'm making 2 copies, I'm doubling it. I'm multiplying everything by 2 to get my new value for what happens if I have 2 copies. That's an important thing to think about as we're talking about today, the ratios, because one of the things we're going to start talking about, and we mentioned the other day, is when things are equivalent. Okay, and that's going to be a key word here, meaning that they are the same ratio. There might be more of them numerically, but it's the same ratio. So this becomes equivalent ratios. We'll get into more of that as we move forward here. All right, activity number 2, a powdered drink mix. Here are 3 diagrams representing 3 mixtures of powdered drink mix and water. So the mix is the white squares and the blue is the water. So in drink mix A, we have 4 teaspoons of mix. So here's my mix, and 1 cup of water. In B, I have 4 mixes, mix, and 1 water. And over here, I have 8 mixes. Oh my goodness, I have 8 mixes and 2 waters. So these ones are a 4 to 1, 4 to 1, and here we have an 8 to 2. All right, so how would the taste of mixture A compared to B? So this is how I'm making them. 4 scoops of mix, 1 cup of water, 4 scoops of mix, 1 cup of water. How would you predict those would taste when you compare them to each other? Well, do you see any difference with how you're making them? Hopefully, you're recognizing they look exactly the same, don't they? Right? 4 to 1, 4 to 1. If I measure everything right, they should taste the same. Everything should taste the same. That's the great part about a recipe. A recipe says if you follow these directions and mix everything appropriately, the right amounts, it should taste the same. Okay? So that's why a recipe works the way it does. It comes out tasting the same every single time, unless you make a mistake, right? So let's look at the next question. It says use the diagrams then we made to complete each statement. Mixture B uses blank cups of water and blank teaspoons of drink mix. Okay, So B uses 1 cup of water and 4 teaspoons of drink mix. So 1 cup of water and 4 teaspoons of drink mix. The ratio, oh sorry, I'm trying to get in 2 screens at once. The ratio of cups of water to drink mix, so the ratio of water to mix, right? W to M is what? Well, the water is 1, mix is 4, so you'd say 1 to 4. Mixture C uses how many cups of water and drink mix? Let's see. C uses 2 cups of water and 8 teaspoons of mix. So 2 cups of water and 8 teaspoons of mix. The ratio of water to mix, water is 2, mix is 8, is 2 to 8. How would the taste of mixture B compare to the taste of mixture C? And that becomes the big question of the day. Okay? So how would the mixture of B compare to C? Well, the ratio of B is 1 to 4, right? And what's the mixture of C? Mixture of C is 2 to 8. Is there a big difference there? Hard to say. Yes, the numbers are different, but in terms of the taste, what will we experience? Well, let's go back and take a look at this one. All right? What would happen if we recognize that in C, yes, I have a lot more ingredients or a lot more scoops of mix and cups of water than the A and B, but what happens if I draw a line right down the middle? What do you notice about this group right here? I have 4 to 1 as a ratio. What about this group? 4 to 1. So all I'm doing in C is it looks like I'm doubling what I did in A and also in B. And in essence, C becomes what I would get if I made a mix A and made mix B and decided, you know what, I think both of these can fit in a larger container. Let's put them all together and put them in C. And so what you end up with is you end up with what we call an equivalent ratio. In terms of the taste, they would be the same, and that's because it is an equivalent ratio. When I take my ratio for B, 1 to 4, and I multiply the 1 by 2 and multiply by the 4 by 2, I end up with 2 to 8. That makes it an equivalent ratio. So what I'm doing to get from here to here is times 2, and here to here is times 2, and because I'm doubling both parts of it, I end up with an equivalent ratio. And that's one of the big ideas from today's lesson. So sometimes you might have different values, but you could still have the same ratio, which means things are going to taste the same. Let's look at this one. Are you ready for more? It says, sports drinks use sodium, better known as salt, to help people replenish electrolytes. Here are the nutrition labels of 2 sports drinks. We have A, we have B. Okay? A couple key things that are different within A and B. Notice that the serving size for A is 8 ounces. The serving size for B is 12 ounces. Okay, so they're not at exactly the same serving size. That's important for this activity. It says, which of these drinks is saltier? Now saltier, we're talking about the sodium. So here's sodium for A, which is 110 milligrams, and B, which is 150 milligrams. Again, if you just looked at it first of all, you'd say, well, that has more. 150 is greater than 110, but this number is dependent upon how many ounces you are drinking. Okay? So we're looking at the number of ounces here. So in the first one, you end up with, in an 8-ounce drink, there are 110 milligrams of sodium. In a 12-ounce drink, there are 150 milligrams of sodium. Now, this is my sodium part here, and here. Now my ounces, fluid ounces, 8 and 12 don't match, right? So it's like having a small container and a little bit larger container and saying which one has more sodium. Well, the larger one would have more sodium, but not because it's value inside of it has more. It's just because there's more stuff to drink there. So what's important is to end up with the same container size. So what I would think about here is looking at the 8 and the 12, the size of the container, and think about the least common multiple that they might have. So if you think about your 8, so you have 8 times 1 is 8, 8 times 2 is 16, 8 times 3 is 24. When I look at my 12s, 12 times 1 is 12, 12 times 2 is 24. I have a common multiple of 24. So let's say I was going to have 24 of these guys, 24 ounces. What does it take to go from 8 ounces to 24 ounces? Well, in multiplication terms, that would be 8 times 3, right? What would it take to go from 12 to 24? That would be a times 2. There's two separate things we're looking at here. So if I multiply this by 3 to get 24, what happens if I multiply the amount of sodium by 3? I'd end up with 330 milligrams of sodium. Over here, I'm multiplying this by 2 to get 24. So if I multiply 150 by 2, I end up with 300 milligrams of sodium. So now when I compare the same size container with the same serving size, which one actually has the most sodium? Well, this one has 330. So we would actually say that A has a greater amount of sodium than B because it has 330 compared to 300 once I get them into an equivalent ratio. Okay? The way it was set up, it wasn't going to be that way. Alright, so it's a great question, a little more complicated there, and one that maybe you might have skipped today, but if you're trying to kind of figure out things a little trickier and work on harder problems, it's a great one there. If you wanted to make sure a sports drink was less salty than both of those, what would you do? Well, if I wanted to get one that's less salty, first I have to know that this is my least salty one here, right? So I'd want to make sure that whatever I did, I'd want to make sure that I ended up using less than 150 milligrams of sodium in 12 fluid ounces. So if I used 100 milligrams of sodium, it would be less salty. So I really want to compare it to B in order to make sure it ends up with less. That's the key thing there. Okay? So that's our idea. Let's take a look at activity 3, looking at batches of cookies, which sound delicious right about now. Alright. Alright. A recipe for one batch of cookies calls for 5 cups of flour and 2 teaspoons of vanilla. Okay. Draw a diagram that shows the amount of flour and vanilla needed for 2 batches. Okay. So one batch means I need flour, 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 5 cups of flour, and 2 teaspoons of vanilla. So that's what I need for one batch. So if I want 2 batches, I'll do another one. 1, 2, 3, 4, 5, and vanilla, vanilla. There we go. So if I'm going to make 2 batches, I'm doubling it, and my diagram will look something like that. Okay, which means I end up with what? I end up with 10 batches of 10 cups of flour and 4 vanillas. Did I change the recipe at all? No, it's the same recipe. I just doubled it from originally having 5 and 2. So I'm making some equivalent ratios there. How many batches can you make with 15 cups of flour and 6 teaspoons of vanilla? So the question there is, if I have 15 cups of flour, let's draw it out here real quick. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. There's my flour. Vanilla. 1, 2, 3, 4, 5, 6. There's my vanilla. We know that this is one batch, this is 2 batches, and this becomes 3 batches. So how many batches am I making if I have all that? I'm making 3 batches. And again, they taste the same. I'm just tripling the recipe. So if I go back to my equivalent ratios, I had 5 to 2 to start with, 10 to 4, and I also have, look at that, 15 to 6, right? So this becomes a series of equivalent ratios. Number 3 then says, how much flour and vanilla would you need for 5 batches? Oh my goodness, 5 batches. Again, I could take and draw another picture, but now I'm drawing a lot of flower boxes, right? That's a lot of pictures to be drawing. Is there a faster or simpler way? Well, let's think about this. When I had the 5:2 ratio and I doubled it, right? And I doubled it. I made it times 2 batches. I ended up with 5 times 2 is 10, and I had 2 times 2 was 4. That worked out pretty well. When I took my original and I tripled it, times 3, 5 times 3 was 15, and 2 times 3 was 6. So whatever I'm doing to one ingredient, I do to the other. Doubling it times 3, and now we're talking about making 5 batches. So what will we need to do to go from having just 5 cups of flour to having 5 times as much? I multiply both ingredients by 5. So 5 times 5 is 25 cups of flour, and 2 times 5 would be 10 teaspoons of vanilla. Does that make sense? So flour is 25 cups of flour and 10 teaspoons of vanilla. All right, and again we can add another number to our ratio chart over here, 25 to 10. All of these are the same exact proportional ratio to make the batch of cookie. I'm just making more as I increase the amount of ingredients I'm using. So, whether the ratio of cups of flour to teaspoons of vanilla is 5 to 2, 10 to 4, 15 to 6, or like we did, 25 to 10, the recipes would make cookies that taste the same. We call these equivalent ratios, and that's our big thing today, equivalent ratios. Find another ratio of cups of flour to vanilla that's equivalent to these ratios. So we've done double, triple, and times 5, so we could do another. If we wanted to make 4 times as much, we could do times 4 everything. So we would say 5 times 4 is 20, and 2 times 4 is 4, right? Oh, sorry, 2 times 4 is 8. Sorry, 2 times 4 is 8. So another one could be 20 to 8, which would be 4 times the recipe, something like that. So how many batches could you make with my new ratio? You can make 4 batches. I chose 4, you could do 6, you could do 10, that is up to you. Just make sure you do it to both ingredients there so it works out nicely. Okay, so let's summarize this real quick. Summarize. A recipe for fizzy juice says mix 5 cups of cranberry juice with 2 cups of water. So 5 cranberry, 2 water. To double the recipe, you would use 10, so if we double it, you'd go 10 and 4. And to triple it, you go 15 and 6. And so we can see with the diagram here we're talking about here, if I double it, I'm doing times 2, times 2. If I triple it, I'm doing times 3, times 3. And I'm taking that one single batch, I'm doing it again and again. So these ratios here are all examples of things that are equivalent. Equivalent. Even though the amounts of ingredients with a single, double, triple batch are not the same, they would all make fizzy juice that tastes the same. So equivalent means they're going to be the same in terms of what they look like, feel like, taste like, all those things there. Let's pause there and take a moment to do our homework, and then we'll come back and check that together in just a few minutes. Alright, homework time for grade 6, unit 2, lesson 3. A recipe for 1 batch of spice mix says combine 3 teaspoons of mustard seeds, so 3 teaspoons of mustard seeds, 3 of those, 5 teaspoons of chili powder, and 1 teaspoon of salt. How many batches are represented by the diagram? Explain or show your reasoning. So in one recipe we have 3 of those. We have 5 chili, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this is 1 and 1. So if I was going to make one batch, I would use 1 of those, 5 of those, and 1 of those. And that becomes recipe number 1, or batch 1. Batch 2, I'd use 1 of those, 5 of those, 1 of those. So there's that one. And our final batch would use what's left there. So how many batches are shown in this picture? I have batch number 1, batch number 2, and batch number 3. So 3 batches are illustrated in this diagram. Number 2. Priya makes chocolate milk by mixing 2 cups of milk and 5 tablespoons of cocoa powder. Okay, so she does milk, and she does milk, and she does cocoa powder with a C. So 1, 2, 3, 4, 5. So that's what she uses to make her chocolate milk. Way to go. Draw a diagram that clearly represents 2 batches. Okay, well, let's make another batch. Sure, we can do that. So there's the milk, and 1, 2, 3, 4, 5 tablespoons of cocoa powder. Just like that. You don't have to get much more fancier than that. I have milk, and cocoa powder, and I'm good to go. So our original ratio was 2 to 5, and of course if she doubled it, it'd be a ratio of 4 to 10, and those are all the same, right? Those are equivalent ratios. You don't have to write that, I'm just drawing it there just to make sure we're on the same page together. Number 3, in a recipe for fizzy grape juice, the ratio of cups of sparkling water to cups of grape juice is 3 to 1. So water is 3 and grape juice is 1. 3 to 1. Find 2 more ratios of cups of sparkling water to cups of juice concentrate that would make mixture that tastes the same. So I want to taste the same. What I'm going to do, I'll take my ratio and I can multiply the same number by the same number. I could double it, so times 2 times 2. 3 times 2 is 6, and 1 times 2 is 2, so that would work there if I wanted to double it. What if I wanted to triple it? I'd multiply everything by 3, We'd have 9 water and 3 of the grape juice concentrate, so those would both work. Those are just 2 examples of equivalent ratios to make the same fizzy grape juice. Describe another mixture of sparkling water grape juice that would taste different. So to taste different, I can really do anything. I could say, well, I start with 3 to 1, and I could say I'm going to double the sparkling water. Let's do that. And then I can quadruple the grape juice concentrate, 6 to 4. Okay? Because I did something different to each ingredient, these are going to taste different. That's the key. It doesn't matter what the number was, it just said I did something different to those. Are there other numbers? There are a million other possibilities for this number, for number B right there. Okay, or letter B. Number 4, write the missing number under each tick mark on the number line. Okay, let's take a look at this one. So, we have this line here, we're missing some numbers here and here. Alright, so how do you go about doing this? Well, a couple ways. We could recognize how much space is between them, but I see that there's some gaps there. So what I'm going to do is I'm going to take the difference here. I'm going to do 30 minus 18, and 30 minus 18 is going to be 12. So I know the distance from here to here is 12, and 30 plus 12 also gets me to 42. So the distance between those two numbers is 12, and this is in the middle, that's half that. What is half of 12? Well, 12 divided by 2 is equal to 6. So I add 6 to 18 to get 24, and I add 6 to 30 to get 36, and now I have my numbers. Okay? Alright, number 5. So, dogs 6, cats 5. Let's make some ratios. Ratio of dogs to cats, dogs 6, cats 5. Cats to dogs, cats 5, dogs 6. For every, how many dogs? 6 dogs, there are 5 cats. The ratio of cats to dogs, 5 to 6. So they're just changing around the order to make sure you're paying attention there. Number 6, Elena has 80 unit cubes. What's the volume of the largest cube she can build with them? Alright, because it's a cube, we're talking about having the same measurement repeated or multiplied 3 times, or times itself 3 times, cubed. So if it was a 2 by 2 by 2, I'd get a volume of 2 times 2 is 4, times 2 is 8. So we can make bigger than that. If it was a 3 by 3 by 3 cube, it'd have a volume of 27. It need 27 cubes. If I had a 4 by 4 by 4, 4 times 4 is 16, times 4 is 64. It's getting closer to 80. And if I had a 5 by 5 by 5 size a cube, 5 times 5 is 25, times 5 is 125. Too large. So the largest cube I can make would be right here. It would be a 4 by 4 by 4 with a volume of 64. I'd have some extra cubes left over, but that is what I would get if I was to make one of those. Right, something like this. Right, perfect. Number 3, oh sorry, 7. Fill in the blanks, make it true. Here we have 3 times its reciprocal. When you multiply by the reciprocal, you end up with 3 over 3, which is the same as 1. 10 times the reciprocal, which is 10 over 10, which is 1. 19 times the reciprocal, which is 19 over 19, which is 1. A times the reciprocal, which is A over A, which is 1. That was exciting. Over here, we want to make it equal to 1. So, what's the reciprocal of 5? 1/5. What's the reciprocal of 17? 1/17. And what's the reciprocal of B? 1 over B. And that is it. That's all we have for today. Have a great day, and we'll see you next time.